Hello IB, here we are starting off 14E, where we're going to look at differentiating from first principles. In other words, come up with a theoretical way of coming out with the gradient function or derivative function. So we can either use first principles, or we're going to use the simple rules that we've already started to maybe guess, and we'll do in more detail in chapter 15. So we're going to look at a general function, f of x, y equals f of x, and we're going to have our 2 points A and B, and look at what happens to the gradient of that chord as B gets closer to A. So A is our first point, x and f of x, and our second point B is going to be h units further along the x-axis. And what we're going to do is B gets closer and closer to A, h is going to get smaller and smaller. So the coordinates of B are going to be x plus h, and the value of the function at x plus h. All right, so up here we've got, this is our x, and the value of the, oops, correction, eraser. So we want to do x plus h. H. We're going to make that a little bit smaller, and f of x plus h. All right, so that's our point. So h is infinitely small, and that way we can find the instantaneous rate of change. So what we're going to do is calculate the rise over the run, the gradient. So remember, if we just show in here, our rise is going to be this part. In other words, how much does the graph go up? And there's our run. So that's our rise and our run. So if we think, what's the difference between the rise, the f of x plus h minus f of x, is just, we can't simplify that any further, whereas the run is going to be x plus h minus x, and our run is equal to h, whatever size h is. So when we find the gradient, we want to find the change in y over the change in x. That's our gradient. And that's how we get our derivative function, by taking the limit of this gradient. Our gradient is y2 minus y1 over x2 minus x1. So our x2 and y2 are going to be, is this point, there's our x2, and that's our y2, and our x1, y1 is our first point, our point A, x1 and y1. So we want f of x plus h minus f of x, divided by x plus h minus x, and we're taking the limit as h gets smaller and smaller. When we simplify that, we come down to h, and that will then give us our derivative function for first principles. So all we have to do is substitute this into whatever our function is. All right, so let's have a look at that. We're going to look at a bit more of the notation, and then we'll look at some examples. So if we've given our function f of x, then f dash x, or you may also use the term f prime x, that's another way of expressing it, defines the derivative function. We could also write that as y dash x, y dash, or dy dx. We say dy dx because it's to do with the change in the y's. All right, so back here where we looked at our change in y, that triangle there is often called a delta. So we could call it delta y over delta x, and that just got abbreviated to dy and dx. So that's where that notation comes from. So we're either going to use, for our derivative function, f dash x, or y dash, or y prime, or dy dx. They're all saying the same thing. Pardon me. Sometimes the dy dx notation will be easier. Sometimes the y dash notation will be easier. So dy dx looks like a fraction, but it's not really a fraction. We don't cancel the d's or anything in it. It's an operator. It's telling us what we're doing with our y function. So we don't cancel it, but it looks a bit like a fraction. So this here we can look at, we have a slightly little value of x, delta x, and they use that delta symbol to represent a small value, delta y. So f dash x is the same as delta y over delta x as delta x approaches 0. So as that small amount approaches 0. And that equals dy dx. So just some different ways of doing the notation. So they're the three ways that we'll be using and you should be familiar with. Voila. All right, so let's do some examples here. All right, so if our function is f of x equal to 5 or y equals 5, that means we've got the straight line going across at 5. What's the slope of that function? Anywhere along that line? Because it's horizontal, we know, probably already worked out that the derivative is 0. So no matter what x value, the gradient of that line is always 0. It's a horizontal line. If we come to this one, f of x equals 3x plus 2, so when we graph it, we're getting a straight line, and our y equals mx plus b tells us that our gradient is 3 all the time, and our y-intercept is 2. So there's our 2. So f dash x in this case is always 3. No matter which x value you take, the gradient of that function is always 3. Can we get that answer from first principles? So here's our rule for first principles. So what we want to do is, we know our f of x is 3x plus 2. Let's now calculate f of x plus h. So that equals, wherever there's an x, we now substitute. It's like a composite function. So we've got 3x plus h plus 2. Expand our brackets and we get 3x plus 3h plus 2. What I then do is we then substitute that in. So our f dash x is going to be our limit as h approaches 0, as that gets smaller and smaller, of our f of x plus h. So that's the 3x plus 3h plus 2 minus our f of x, which is just 3x plus 2. All divided by h. So we need to write this down again. It does get a little bit tedious. Limit as h approaches 0. So now, if we're going 3x minus 3x, then that cancels with that. Plus 2 minus 2, so they will cancel. So you can see now, all we're left with is our 3h. And that's gone fat again. We need to save it over h. We now see that the h's cancel, so we end up with our limit as h approaches 0 of 3. And because there's no h's in it, then that limit, no matter what h is, whether it's big or small, will be 3. And that was the same answer that we got before, just from knowing our y equals mx plus b. We knew that already. So we could see that one easily, but that's just a method for using that formula of our limit. So in this case, our gradient function is going to be a straight line at 3. All right. What we can then do is do this for any function. So we're going to leave this one. See if you can have a go at working out what is f of x plus h. And what I tend to do is, let me just get you started, then you can have a go at this. We've got that blue, a bit smaller. All right, I tend to write out f of x plus h because that fraction gets quite complicated by the time you get these sort of functions in. So I do this to start off with, x plus h squared minus 3. So I expand that, and then I calculate down here f of x plus h minus f of x. I do that calculation and then substitute it into this equation. That just makes it look a little bit simpler. So have a go at that, and then we'll look at this one in class. We've got room to draw our f of x function here, so you can sketch that up if you wanted to get a head start, and then we'll sketch our derivative function. Another way of doing this is if we wanted to find a value of the derivative at a particular point, in other words, we wanted f dash of a, so what is the value at a, then we could start off with that straight away. So if I come back to this previous example, here we've got f of x of 3x plus 2. I could ask on this one here, if I've got f dash x equals 3, I could then write, well, what is the derivative at 1? Because there's no x's to substitute in, it's still 3, and we know that for this function it's always 3. But we can calculate the derivative at a point, and that's the notation. So in this example here, what we're doing is calculating the derivative when it's at a general point A. So our derivative function then becomes f dash of a equals the limit as h approaches 0. We're still getting that smaller. But now instead of writing x here, we're putting our a value in. So f of a plus h minus f of a, all divided by h. And we can do this calculation from all the first principles. Calculate f of 5. So that's just going to be 5 squared plus 2 times 5, which is 35. F dash of a is going to be the derivative, is the limit as h approaches 0 of f of 5 plus h minus f of 5 divided by h. So now substitute your 5 plus h into your function. So the function here is x squared plus 2x. So we get 5 plus h squared plus 2 times 5 plus h minus the 35, which is the f of a, divided by h. Expand, so you need your quadratics again, so expand that, expand this bracket as well. So now we see the 25 plus 10 cancels with the minus 35. We also can't see anything else that cancels. Oh yes, we can. The plus 10h and the minus 2h, and they don't cancel, they add together at least, so we end up with h squared plus 12h over h. Factorise, so we can cancel. So we're left with h plus 12. As h approaches 0, then we're left with just 12. So that means the instantaneous rate of change of the function at 5 is 12. So that saves it doing it with x and then substituting. So we'll have a look at using our calculators again, and then we'll have a look at this other example, which is even more complex, just to get your practice with it. So thanks for listening. Make sure you've got some good notes on this and come to class ready to have a go. Thanks. Bye for